If you're watching this podcast, it's probably because you were absent from class today. A lot of AP exams going on, but I went ahead and lectured for even block day anyways about the heat of fusion and about a new concept called entropy. So go get your PowerPoint notes, be ready to take some notes. It'll be very helpful if you have a calculator as well. So what we've been doing so far is talking about heat for either a chemical change or heat when there's a change in heat but not a change in phase. This is a bit of a rerun because we're going to discuss heat of fusion and heat of vaporization. And so the heating curve for water that you see here should look familiar because it was discussed back in the intermolecular forces chapter. So heat of fusion can be expressed either on a calories per gram or on a kilojoules or joules per mole. So let's define what heat of vaporization and heat of fusion is. Heat of vaporization is the energy needed to vaporize or boil 1 mole of any substance. This graph was for water. And the heat of fusion is just a fancy word for saying the heat that's needed to melt 1 mole of ice. So no longer can we use m times c times delta T. That's only for when there's no phase change. These are the values that you would need to calculate how much heat is needed to melt ice or to vaporize water, and it's a very simple kind of calculation. You would always be supplied these values. You'd always be supplied these values. That's the heat of fusion of ice, and that's the heat of vaporization of liquid water. Notice that that's much larger because remember, when you want to vaporize something, you have to break all of the intermolecular forces. When you're melting something, you're just breaking some of those. And so you would always be giving these heat of fusion of ice and heat of vaporization of water, not expected to remember that. Essentially, since it's expressed in kilojoules per mole, all you need is to have the moles of your substance, and the biggest challenge I might throw at you is give you grams instead of moles. So of course, the molar mass of water, I hope you've memorized it now by the end of the school year, is 18. So if a problem asks you how much heat is required to melt a 15-gram ice cube at 0 degrees Celsius, I'm hoping your first reaction is to turn grams into moles. Then you'll leave that number in your calculator and you will times it by the heat of fusion for ice. So here's the setup. Take a moment, crunch those numbers. You're going to have less than a mole since 15 is smaller than 8. And when you do your number crunching, moles will cancel out, so at the end, all you'll be left with is kilojoules. That's right, I'm waiting for you to do the work. By the way, notice that it has an ice cube at 0 degrees to give water at 0 degrees. They're making sure they limit you to just how much heat it would need to melt that amount of ice, not how much heat would be needed to begin to warm up the ice water that would form. So here's your answer, 5.0 kilojoules. Our second problem is going to be a heat of vaporization problem. You have to add heat to vaporize something, but you can remove heat to cool it from a vapor back down to a liquid. And that's the basis of question number 2. It's still 15 grams of water, but this time it's in the form of steam. So you can use that mole calculation you had from question 1. And this time we're going to maintain it at 100 degrees so we can see just how much heat would be needed to be released or removed to cool off 15 grams of steam and turn it into water and then just stop there. So we have to go get our molar mass of water and turn grams into moles, and then we multiply by the much larger heat of vaporization for water in the form of steam. Moles will cancel, grams will cancel, your answer in kilojoules is 34. So that's how you deal with heat of vaporization and heat of fusion problems. This was for water. Each pure substance has its own constant. I'm now going to ask you to skip ahead in your notes to find the section that is about what we call entropy. It starts here at slide 49. I'm not sure what the Roman numeral number is, but we'll come to it in just a moment. So turn a page or two and find the section about entropy. Entropy is the other driving force in the universe. So far in the chapter on thermo, we've only been looking at enthalpy, heat content. But there's another driving force, or hindering force, that's called entropy, and it has to do with the degree of disorder. Don't say the word organized, don't say the word order. The word you're looking for is disorder or disorganization. Well, water always wants to go to its lowest energy state. It flows downhill. Roads do not build themselves over time. Roads fall apart over time. If you're lucky enough to live in Florida, you might come out one day and find one of these guys. It's called the sinkhole, caused by the undermining of the highly carbonate kind of components that make up the soils of Florida. They've depleted their groundwater, and or acid rain can eat away at those caverns. So you might come out and find your car at the bottom of one of these pits. Not fun. But roads fall apart, buildings fall apart, and things in the universe tend to get quite messy. You don't come home from school to find suddenly that all of your clothes are off the floor and hung up in the closet, assuming you have no maid or mother unit that does that for you. Things in the universe get messy, and that messiness is called entropy. Be careful with the spelling. Entropy is different than heat content, which we've been studying, enthalpy, and it can influence the direction of a chemical change. Now here's a simple reaction showing, it's not even really a reaction, it's an ionization or dissociation. Salt can dissolve in water. It's an endothermic reaction, and the problem with endothermic reactions is usually the universe doesn't favor them to happen. That's because you're taking heat from the outside and putting it into the bonds of the products, and you go from a low enthalpy to a higher enthalpy. That's heat content. Usually that's not favorable, but you know that your common sense tells you that even though this is endothermic, salt dissolves in water. And the reason is because you are increasing the entropy. Specifically, 1 mole of salt makes 2 moles of ions. And anytime you have more than, you're making more products from the original reactants that you started with, you're going to increase entropy or disorder. Now I'm grabbing a piece of paper there because I'm getting ready to do a little demo here. So here's a solid block of salt. I'm not sure it's salt, but let's pretend it is. And over on the far right, that's what salt looks like when it's all dissolved. Pretty messy. That's what entropy is. The universe prefers reactions to go if they create products that are more disorganized. So we call that entropy. We have a new symbol. Don't ask me why it's S, I don't know. Change in entropy is delta S. Our units are joules per Kelvin, but more commonly joules per mole Kelvin. Not kilojoules, joules. Come back to that later. Why do we have to put the temperature in there? It's because you know, and I know, that the more hotter a substance is, the more wild and crazy its action is, and so the more disordered it is. So whenever we specify in tables a certain entropy value, it's always specified typically at 25 degrees Celsius. So we can get entropy more disorder, increase in entropy, when more molecules are present that were produced than were present when you had them in the reactants. 1 piece of paper, 2 pieces of paper, 4, 8, very messy. When you have more numbers of things, you have a greater possibility for them to be disorganized. We call that degrees of freedom, but you'll learn about that if you take AP chemistry. So that's one way you can make entropy increase. When you change a solid into a liquid, or turn a solid into a liquid into a gas, you're clearly making more disorganized forms of matter. And we've already discussed that when you make a solution by dissolving a solid or a liquid in another solvent, you're creating more entropy, more disorder. So negative delta S means a decrease in disorder. Please don't say this, increase in organization, put less disorganized. In fact, draw a line through that right now. You're decreasing the disorder when you have a negative sign. But when you put a positive sign in front, That means you're increasing the disorder. There's more randomness, more disorder. And what we'll do right now is predict, and then I'll give you a chance to practice whether this change in entropy is positive or negative, and then you can check your answer. So our first equation that you see here shows one solid substance turning into two solid substances. What do you think? More or less disorder? Think of the paper demo. If you said more, you're correct. When you make more numbers of molecular products, two different things have all other different kinds of ways they can be mixed up in each other than if you just had a substance that consisted of one type of molecule. Now examine the next equation. I can't use the form of matter because they start as gases and they end as gases, but now count the total number of molecular reactants. 1 nitrogen and 3 hydrogens makes 4 molecules on the left. On the right, you clearly have 2. So making fewer numbers of molecular products means that you're getting less disorder. So you would want to put in a negative sign next to that equation. And finally, the last one's kind of tricky. N2 and O2 makes 2NO. Bummer, they're all gases, and bummer, there's 2 on the left and 2 on the right. But would you agree with me that there are 2 of same things, 2 molecules of nitrogen monoxide on the right, but on the left, there's 2 molecules of different things. So when you're going from different into same, that's less randomness, less disorder. So we should have a plus, a minus, and a minus. Now we're not just going to ask you to predict if the delta S is getting more disordered, positive, or less disordered, negative. We're going to ask you to use a version of that products minus reactants equation that should look very familiar. You'd have an entropy table. If you look carefully on your PowerPoint notes on the bottom right, you can see there's a table of entropy that shows many different substances at a specified temperature. Please find right now, look at that table, find an element. Take a moment and look at it. Remember when we did delta H, how the heat or enthalpy of elements, their heat of formation was 0? That's not true for entropy. All substances, whether they are elements or compounds, have some innate form of entropy. So you can't get to use that 0 rule anymore. But the rest of the rules are the same. You'll still go products minus reactants, being sure to multiply any values if there are coefficients in the equation. Here is a sample problem. When I take 2 moles, remember it's products, so I have to go 2 moles of ammonia times its entropy, joules per mole Kelvin. There's no other products, so I subtract the sum of the 2 reactants, 1 mole of nitrogen and 3 of hydrogen. That's why we multiplied here. Those values all came from a table to give you your final answer. I would not write joules/Kelvin. I would write negative 198.3 joules/mole Kelvin. That's typically how we do it. So it's just like what we've done before. In your PowerPoint notes, I'd like you to take a moment and solve the 2 liquid water into 2 hydrogen gas and 1 oxygen gas. And when you come back to class, you'll be able to check your answer if you'd like. The other equations that you see there, sadly, some of those components are not in that table, but notice that we've given you some answers on the PowerPoint, and you could go look those up in the back of your textbook, and you'd find the entropies, multiply them by their coefficients, products minus reactants. It's pretty easy. So what I need you to do now, as we get to the end of this vodcast, is please go find a page in your packet that has about 8 or 10 questions at the start that ask you to predict, is this a positive S or a minus S? Is it getting more disorder or less disorder? The page number escapes me. It's 20 something, I think, but big help that is for you. And when you come back into class, I'll post those answers and you can double check. That's it.